morning to everyone. Good morning to all the speakers in the speaker room and also to the participants that are listening to the stream. Welcome to our session on quantitative precipitation nowcasting. My name is Cynthia Kabachai-Henken. I'm from the Free University of Berlin. And together with my project colleague, Ricardo Reynoso Rondinet from the University of Bonn, we are chairing this session this morning. So before we start with the session, I would like to point out a few things regarding the organization of the session. So first of all, we would like to kindly ask our speakers to please consider the speaker or the time of about 50 minutes for the talk and about 5 minutes for questions. Further, please mute your microphone when you are not giving a presentation or asking a question. To all the listeners, please use the Slido system to ask and upvote questions, and do not forget to fill in your name. And we will gather the questions to address them directly after the talk, or also use them in a discussion session at the end of the session, and also for tomorrow afternoon where we have a discussion session. Okay, so in the corresponding QPN video chat room, you can also ask questions in the chat, and you can ask to be transferred to the speaker room. So you can ask your questions directly yourself, or we can read out the questions in the speaker room here. Okay, so that's from my side for now. So please, Ricardo, you can continue.
Thank you, Cynthia. Good morning, everyone. Thank you for joining the RealPEP conference. We are almost ready. We're waiting for solving some technical issues of one of our speakers. So I would like to kindly ask everyone to wait for a few more minutes until we solve this problem so we can start with the QPN session. Thank you.
Can you hear me?
Yes.
Yes, yes.
Good, okay. I'll try not to touch anything before I lost the connection.
Okay, so I'm glad to hear that Loris is here with us in the speaker room. So Loris, are you ready, or do you?
I'm ready, yes. I'm about to share the screen.
Okay, let's see if maybe there's also some problems, maybe. Okay, I think it's gonna work. Yeah. Okay,
can you see the first slide?
Yeah, so Loris Foresti will be our keynote speaker of the QPN session this morning. He's coming from Metro Swiss, and we're happy to have you, Loris. Please go ahead.
Thanks for inviting me for this keynote presentation. I made a summary of several contributions from people from Meteo Swiss, not only those who are listed as co-authors, but also several students that work here. So the co-authors of the presentation are Daniele Nerini, my old PhD student, Ulrich Hamann, Alessandro Hering, Yannis Sideris, and Urs German. And today we are talking about nowcasting of radar precipitation, growth and decay in complex orography. And I will put the accent on probabilistic machine learning approaches. So the talk is structured as follows. There will be first an introduction to probabilistic precipitation nowcasting using traditional methods, I would say. An example with the library PySteps. Then there will be a chapter on orographic precipitation nowcasting, and there we will show both deterministic and probabilistic machine learning models. And the next chapter will be about convective cell nowcasting, and also there we will split the chapter in two parts, deterministic and probabilistic machine learning models. And at the end, I will try to wrap up a bit the findings of all our studies. So if you want to do nowcasting, you need data first, and the data in Switzerland are produced by C-band dual polarization radars. There is one in Montelema that was renewed in 2011. There is a second one in La Dole above Geneva, also renewed in 2011. One in Albis, and all these 3 radars have been upgraded to dual polarization. There is a new site in Valais, Plaine Morte, a radar at 3,000 meters above sea level since 2014, and another one in Canton Graubünden, Grisons, also around 3,000 meters or slightly lower. And we now have a network of 5 C-band radars, dual polarization covering the Swiss territory. What you get out of this, it's a radar image with precipitation intensities. And if you're lucky enough or unlucky enough, like it happened on Friday, you can accumulate radar images over 24 hours. This is a radar rain gauge combination. We basically we passed 400 millimeters in 24 hours last Friday. And the lake not far from my apartment has started to creep towards my building. So once you have radar images and you want to do nowcasting, if you want to do it easy, you can do it at home and download the PySteps library. I'm doing a bit of advertisement here. PySteps is an open source research platform for radar precipitation nowcasting. It's written in Python. It's available on GitHub, and now it has more than 20,000 downloads. And it was a joint development of Meteo Suisse, the Finnish Weather Service, Australian Weather Service, and McGill University. And now we have more and more users and contributors to the library. There is also a nice development that now PySteps has become the operational model in the RainViewer smartphone application. And it is used by several other companies, weather services, and universities. It contains basic modules for reading different radar data formats and to writing out nowcasts in netcdf format. For example, data processing, several optical flow algorithms, and how to extrapolate fields. Stochastic simulation to generate ensembles, and also forecast verification. Here are a few examples of the PySteps library. You see here on the top left different ensemble members for a nowcast at plus 10 minutes. You see that they more or less agree on the location and intensity of rainfall. If you go at plus 60 minutes for this convective situation, you see that there is a lot of disagreement between the different ensemble members. And here on the bottom right, you see one single member, how it evolves through time. And the goal is to make this extrapolation evolve. So to exploit first the Lagrangian persistence, the fact that precipitation persists over time when it's extrapolated, and then add stochastic perturbations so as to represent the forecast uncertainty. From the ensemble members, you can also compute the fraction of ensemble member exceeding a certain threshold, for instance, 2 millimeters per hour. And here we see that the probabilities are quite sharp, either 0 or 100%. And after 1 hour, the distribution is much more homogeneous, which reflects the uncertainty in the nowcast. So this was a brief but speedy introduction to probabilistic nowcasting. Now we are going to nowcast orographic precipitation. So all the previous nowcasts that you do it deterministic or stochastically, they're not able to understand whether precipitation will grow or decay in a systematic manner. But over the Swiss Alps, you see here a situation with northwesterly flows approaching the Alps. And then you see that they don't pass the Alps. There are firm conditions with dry winds on our side of the Alps. But if you do an extrapolation, stochastic or deterministic, it will just pass the Alps. Basically, the radar extrapolation is completely blind to orography, and this is what we want to solve with machine learning. So this growth and decay, how do we define it? So basically, it's the difference in precipitation once we subtracted the motion. So we define boxes over the domain of 64 by 64 kilometers, and for each box we computed the mean aerial precipitation. And then based on optical flow, we move the boxes further in time, or from the destination box we go backward in time to pick up the origin coordinates of the box. And we compute the multiplicative difference between the mean precipitation at destination, for example, here, uphill, and the origin over the flat plains. And this growth and decay is represented in decibel units. Basically, if it's 0, there is no change in precipitation. If it's +3, we double the amount of precipitation. If it's -3, we halve the amount of precipitation. It represents the Lagrangian rate of change of precipitation, to be a bit more formal. And this definition can also be applied not only to boxes, but also other variables. And you will see later that we can also use similar definitions for the convective cell severity and how it changes along the motion. We apply this, we extracted this box over a long data set of several years. And we ended up with 22 million boxes. These are the samples, and 7-8 predictors. So for each box, we know the geography, the coordinates, the flow direction, the freezing level height. We represented the diurnal cycle with 2 trigonometric variables. We know the precipitation at the origin, the destination, and the growth and decay. And this is what we would like to predict using all these variables. These maps are average maps over the whole archive, non-stratified. So we take the average growth and decay at a given pixel for all the flow direction. And you can see already that there is quite some spatial structure with growth of precipitation on the upwind slopes of the Alps and decay of precipitation in the inner alpine valleys. You can also notice that boxes or precipitation are moving much slower on the southern side of the Alps than over the flat areas of France. And finally, this is a wind rose of these boxes, just showing that they mostly come from west or southwest. So this is nothing, it's not really a surprise, I would say. But now we can go a bit further. We can say, okay, let's take the average growth and decay for all the northwesterly flows with a freezing level height between 1 and 2 kilometers. And then we can do the same with southwesterly flows. We suddenly see that the patterns are very different. With southwesterly flows, we have growth of precipitation once it's moved over the Alps. And with northwesterly flows, the growth is on the other side of the Alps, like we saw in the example in the first slides. So if you formalize this stratified, can you hear me?
Yes. Yes.
Okay, I have a weird sound in my headphones. Do you hear that sound as well?
No.
No.
Okay, wait a moment.
The system is not able to pick up your computer sound, only your microphone.
Oh, if you can still hear me well, I can continue to speak, but I have a disturbance in my headphones. Okay, it's finished now. Good.
Okay.
There was an alarm, kind of an alarm sound in my headphones. Okay, good. It was quite disturbing. So we can reformulate this stratified climatology by computing the conditional expectation of your variable y, your growth and decay, conditioned to certain predictors in a certain interval. If you want to reduce the interval to 0 to be very precise and very about your conditions, then you basically end up having to estimate a function f, which depends on predictors. And this is no different than fitting a regression model to the data. So basically, if you want to reduce your freezing level height from an interval of 1 to 2 kilometers to 1.5 kilometers exactly, it turns out to be just trying to fit a regression model to the data. And this is what we did with a neural network. We used as predictor the location, the flow direction, the freezing level height, the diurnal cycle, and as predictant, the growth and decay. Once you train the model, you can do some interesting exercises. For example, you can cut through the space of predictors and say, let's fix the freezing level height at 1.5 kilometers. Let's change the flow by 5 degrees at a time, and let's see how the prediction of growth and decay looks like. Here you see the vectors. So now we have a southwesterly flow with growth of precipitation here, westerly flow, northwesterly flow, growth here and decay in the Alps with Föhn on the south, northeasterly flow. So you can really study the dependence of growth and decay with flow, with freezing level height, with different variables of your phase space, just by playing with the machine learning algorithm and generating synthetic fields of predictors. So now this concept of growth and decay is used in the MetaSwiss app. It's already operational by the now Percip algorithm developed by Yanis Sideris. But instead of being predicted with machine learning, we extract it in real time from NWP fields. So if you want more details about this, you can ask Yanni. There is also another study that was done by a collaborator in Italy, Gabriele Franch. He went a step forward. Instead of using only classical machine learning, he used convolutional neural networks, recurrent as well. And here you see an example where you have an observed radar field in Trento, North Italy. This would be a radar extrapolation using a classical PySteps library. And this is the prediction using the deep convolutional neural network. You can see that the field is much smoother, but that the neural network managed to capture this growth of thunderstorms and this southward propagating line of thunderstorms. In general, the neural network, which is represented here is in orange, performs better than classical radar extrapolation, which was also smooth to match the scales of the neural network. But there is a significant wet bias, and the forecast field becomes smooth. We also still need to verify whether this forecast is able to reproduce the growth and decay fields that we observed in our climatology. But this was just a deviation to show that there is potential in deep convolutional neural network for nowcasting, but there is still work to do to compare them with traditional extrapolation nowcast. Okay, now we can move to the probabilistic machine learning. As you saw in the previous slide, there was a very smooth nowcast, and this is an expected outcome every time you try to minimize a mean square error. Because if you minimize a mean square error, you end up minimizing the variance of the predictions. So there is no way using deterministic machine learning to avoid smoothing the forecast. You can change the cost function, do some tricks here and there, but it's something that is quite unavoidable. And here you see a scatter plot of the observed growth and decay and the predicted growth and decay, and you see that the range of the predicted growth and decay is much smaller than the range of the observed growth and decay, which is called conditional bias. So the elegant way out from this situation is to predict the conditional distribution of growth and decay instead of just the conditional mean and move to the probabilistic world. Our first attempt in this direction was to create a quantile artificial neural network. And for this, we first trained a decision tree and optimized its hyperparameters using a validation set. And then we looped over each leaf of the tree and computed a set of quantiles, 5%, 50%, 95%, from the target values of each leaf. So we will have, at the end, several growth and decay values, several quantiles for each leaf. And at the end, we used we used another neural network with multiple outputs, one for each quantile. And this neural network was trained on the training set and on the validation set we used early stopping. So to represent this, this new model, here you see a synthetic example with the one single predictor, X, and a varying level of noise, and this is the variable to predict. The decision tree, if you ask the prediction interval, for example, the difference between two quantiles, you will have quite a stepwise function, which is not that nice to see, and it will not be nice to see on our growth and decay fields. And what the neural network does is basically to interpolate the quantiles from the decision tree. And also, the neural network allows to be robust to the outliers, for example, this point here. So basically, this quantile neural network is quite a naive method. It benefits from the computational speed of the decision tree, but also can impose the smoothness from the neural network, which is quite nice. If you verify this benchmark, here you see the observed quantile, the predicted quantile. You see that the decision tree has some departures from the perfect line. The number of points falling within a certain prediction interval is also smaller, 40% instead of 50, 84% instead of 90. And with the Quan, we can improve all scores. If we now move to the real case, here I show prediction maps of the 90% prediction interval of growth and decay for low freezing level height. Here for high freezing level height, for example, in summer. You already see there is a difference between more winter condition and summer conditions. The uncertainty is much higher in summer because a thunderstorm typically will change over the next hour much faster than stratiform precipitation during winter. And also there is quite some spatial detail. It seems to be less predictable over France and more predictable over the Swiss Alps. And what is important to see is that in the previous maps of growth and decay, the deterministic forecast, we had values +2, +3 dB of growth and decay, and here the uncertainty is actually +10, +12 dB. So the uncertainty in predicting the growth and decay of precipitation is much higher than the systematic change that can be inferred from orography or other predictors. Here we verify again the quantile neural network using real data, the observed quantile, the predicted quantile. It works very nicely. And this is a last plot where we sorted samples by the prediction interval, low prediction interval and high prediction interval, high uncertainty. And then we just represented a few samples from the validation set, or actually the test set. And if you represent in gray the 98% prediction interval, you would expect 2% of the points of the observation to fall outside. And if you count these 1, 2, 3, 4, 5, 6, 7, 8, 9 points, it ends up being 1.8% of the points, which is also a nice result. Good. So I hope I was not going too fast because we have quite some slides. Now we can move to convective cell nowcasting. And here I will present the work done by my colleague Ulrich Hamann and a series of students who did an internship at Meteo Suisse, in particular Joel Zeder and Shruti Nath. So now we will be scaling up the number of predictors, because in my orographic precipitation example, we have 7, 8 predictors. And here they created a huge data set with radar variables, satellite variables, Cosmo, lightning, and also, of course, topography and location and time of the day. There are many, many different variables from the radar. You have vertical integrated liquid, for example, ecotop height, 20 dBz, 45 dBz, probability of hail. From satellite, we have water vapor channels, infrared channels. From Cosmo, we have instability indices. And also we have some nowcasting sub-products like cloud top height, cloud top pressure, and temperature. And we computed the motion of the radar fields using pi steps, again, which can be used also to nowcast the future position of the thunderstorms. And then using pi steps, you could track in the past the thunderstorm and then retrieve all the predictors along the trajectory. So the goal is to improve nowcasting, not only just doing an extrapolation, the thunderstorm will be at this location after 30 minutes, but also trying to infer whether it will grow or decay. And for this, we will use the XGBoost machine learning model. Some more detail here. We use the thunderstorm radar tracking algorithm to first select which thunderstorm we are interested in. We track the position of this thunderstorm backward in time with pi steps over 45 minutes. And for each predictor, for each field in the previous slide, over a 24-kilometer diameter, we extracted different statistics, the mean, sum, standard deviations, minimum, maximum values, different quantiles. And this was done for every variable. So we ended up with more than 8,000 predictors, 68 radar, satellite, and WP variables, 10 time steps, going back 45 minutes, and then 12 statistics. And the goal is to predict the TRT rank up to 45 minutes. And the rank describes, it's a combination of different variables that describes the thunderstorm severity. In green if it's moderate, in yellow if it's severe, or red very severe. And this is used in our automatic thunderstorm warnings. And here on the right you see an example of the satellite brightness, temperature, the maximum, minimum, and median, I think. I cannot read very well, for one individual cell along the trajectory. And the same for the rain rate, and you can do the same for all the variables that we extracted. Just a few words on XGBoost. I must say that I'm not an expert in this model. It's roughly equivalent to a random forest, which is an ensemble of decision trees. The difference with random forest is that XGBoost builds only weak decision tree, not very complex but decision trees, and boost the decision trying to focus on the samples that are difficult to predict. So during training, these samples are that are not well predicted are weighted more, and then they are combined in the final solution. And a nice feature of this model was done by Shruti was to extend XGBoost also to estimate quantiles. And she made some interesting studies to change the cost function, the quantile cost function to simplify the training and to make it more efficient and to avoid being trapped in local minima. But if you remain in the deterministic world, with XGBoost, it's quite easy to extract the importance of variables. This is a ranking of the importance of different variables. You see here the radar, the satellite, and WP and lightning. You see that in the first positions you have the area, for example, of maximum radar reflectivity above 55 dBz, even 45 minutes in the past. You have the max radar reflectivity 5 minutes ago. You have a severe satellite channel, 9.7 micrometer, 15 minutes ago. So you have different variables. It could be a bit cumbersome to look at every individual variable, so you can combine them together and really look at individual data sources, how much they contribute to the forecast skill. You see here the forecast lead time, up to 45 minutes, and the relative importance of features. If you take the first lead time, you can see that radar features, as expected, are the ones bringing the most skill to XGBoost to now cast the evolution of this thunderstorm rank, followed by NWP, then satellite, lightning, and topography, location, time of day, season. But very soon, after a few tens of minutes, NWP variables take over, and they determine our ability to predict the evolution of the thunderstorm, which is a very interesting finding because it tells us that now we have to move beyond just using radar observations or a combination of radar and satellite observations for nowcasting, but we can also integrate NWP variables. So some verification. Here we use a Taylor diagram. I don't know if you're familiar with it, but it's normalized. This is the standard deviation of the observations. So all the predictions that maintain the standard deviation of the observation, that is, that don't have this effect of conditional bias, will follow this line. And all the predictions which will lose variance and become smoother will go along this path. And you can see that also XGBoost nowcast, as it was the case for artificial neural network, shallow or deep or whatever neural network you're using, you end up having conditional bias, you end up having a smoother prediction. So somehow it's the price to pay. You have a smaller root mean square error, but then you also have a smaller variance in your predictions. One way out that is quite simple would be to use probability matching. So we would take the smooth prediction by the machine learning and match the cumulative distribution of this forecast with the one of the observations, so that we obtain the same histogram. So in this way, we can recover the lost variance, and it's what we see here with this sign. And what is nice to see is that probability match results still have a smaller root mean square error than a pure nowcast based on persistence, which assumes that the thunderstorm rank will remain the same for the next 45 minutes. So a combination of, okay, we do a deterministic machine learning, we end up smoothing the forecast, we try to recover the lost variance by probability matching, and despite that, we still remain with lower root mean square error. So this is a positive result. And if we now move to the quantile prediction, I just show a couple of examples that were produced by Shruti. This is a +5 minute nowcast of the thunderstorm rank. So here you have moderate thunderstorm, severe thunderstorm, very severe thunderstorm. In blue, you see the 90% prediction interval. In green, which is narrower than 50% prediction interval. And in red, the 33% prediction interval, which is even narrower. And in black, you can see the observations. So you can see that most of the time, the observed TRT rank falls within the 90% prediction interval. And if it's well calibrated, only in 10% of the cases, the observations, like in these 2 points, they would fall outside of the prediction interval. If you now move to a 30-minute nowcast, now we can see that there are more observations falling outside of prediction interval. And you also can see there is a tendency to underestimate the TRT rank, also for the probabilistic model. And this is some sort of regression to the mean, because if you want to predict a thunderstorm at plus 30 minutes, so plus 1 hour, it's much safer to say the thunderstorm will probably decay within the next 60 minutes. It will not last for hours with a TRT rank of 4 and destroy everything along the path. So the likelihood for the thunderstorm to remain so severe decreases as you go into the future. Okay, try to move now to the conclusion. I have here 3 slides. First, I try to kind of classify different nowcasting frameworks. First into deterministic nowcasting framework, and here we can also subdivide into variance preserving, like when you extrapolate a radar image and you don't smooth anything. And this is similar to, for example, the control member of an NWP forecast. Then we have another deterministic forecast, which is error minimization. Here you can obtain this by machine learning, by minimizing the mean square error. You can obtain it by extrapolating the radar field and using pi steps or a Fourier transform to filter out unpredictable features. And this would be similar to the ensemble mean of an NWP forecast. Then you have 2 probabilistic frameworks. One is quantile based, what we have shown in this presentation. And this would be like having the probabilistic forecast from an NWP model, but not having access to the ensemble members. You only have the point probabilities. And then you have probabilistic methods that I didn't really explore much into this presentation. There was only one example at the beginning based on stochastic methods. And these are ensemble based. So we generate realistic realizations of the atmosphere, and from them you can extract the probabilities of exceedance of different thresholds. And these probabilities are also area probabilities, because we can do that over catchment and different regions. So if you want to compare machine learning with methods in PySteps, you have to choose methods from the same nowcasting framework. So if it's not fair, for example, to compare an artificial neural networks, also deep artificial neural network, random forests, to a variance preserving extrapolation forecast, because of course the mean square error will be higher because we are trying to maintain the variance. So we should rather, as it was done by Gabriele, compare with the SPROG model, which filters out the unpredictable features with time. And same with probabilities. If we want to compare our probabilistic machine learning based nowcasts with PySteps, we should take probabilistic models from PySteps. And finally, and this study was not really done yet, or not completely, if you want to compare stochastic PySteps nowcast to machine learning, we should go into the world of generative machine learning. And I have a slide on this. For example, generative adversarial neural networks, they are designed to produce stochastic realizations of fields, of images, videos, and also precipitation fields. There is a generator that learns how to produce these synthetic examples. And then there is a discriminator that learns how to distinguish these generated examples from the real image. And here there's an example of Jussi Leinonen. I'll try the YouTube animation, but before trying that, here is a real radar field over Switzerland. It was downsampled to a lower resolution, and then the guns were used to re-inject the variability at high resolution to create this so-called super resolution. And you can generate many realizations from that. Okay, maybe we continue. It's not very important to have the animation here. What we still need to do in this context is to see if GANs are not only able to produce realistic precipitation fields, this was demonstrated very well in the paper, but also if they are able to learn the systematic growth and decay patterns. And also if the probabilistic nowcasts are reliable and calibrated in comparison with stochastic nowcasts produced by PySteps. So in a final slide, in my abstract, I have listed some questions. I condensated them here, and I try to answer now. So which are the sources of predictability of precipitation growth and decay? You've seen for orographic precipitation, the location is very important, the flow direction and speed, the freezing level height, or even air stability, you can bring that to work forward. For convective precipitation, we learned that there are not only radar variables important, but also in WP, and the importance tends to increase with lead time. Satellite variables also bring a tangible contribution, and lighting variables and location are less relevant. And this is something that we also found in the orographic precipitation study. In summer, precipitation is much less predictable, much less systematic with orography than in winter conditions. How to reduce the number of predictors? And here I will be a bit provocative. You can follow different strategy. For example, feature engineering with expert knowledge. So you start small with a small number of predictors that you choose yourself. You have control on what the machine learning model is doing. You can start big with many predictors and then use some feature selection to discover which are the important ones. And you can discover interesting things there. Or you can go to the world of deep convolutional neural network with recurrent layers. And I have to admit that I'm not an expert there. And this is a step to avoid feature engineering. So you hope that your convolution layers will learn the spatial dependencies so that you don't have to do feature engineering yourself. But the issue is that you may end up with a model and an architecture that is so complex that it's hard to interpret, but you will probably perform and outperform other models. So there is some work to do in this type of models to become more interpretable. How to perform a fair comparison between machine learning and extrapolation-based nowcasts. First, you need to compare methods from the same nowcasting framework, or alternatively, normalize mean square errors, or compare fields at the same spatial scales, for example, with wavelets or Fourier transforms, so that we compare apples with apples. And how to go beyond these smooth machine learning predictions that are the first things that we encounter when we try using machine learning for nowcasting. One approach is to post-process stochastic simulations, for example, based on Fourier transform and pi steps, using the quantiles by machine learning. And this is a work that is yet to be done. And another step, and this I think is the way forward, is to use the generative machine learning framework, which tries to do both at the same time. So you don't have to go via a Fourier-based stochastic simulation, then post-process this nowcast based on the quantiles by machine learning, but you can do everything in one shot. So there's a lot of potential there. And finally, not to forget, machine learning is a modern algorithmic-oriented statistical tool to interpolate or simulate, if you're generative, analog states in a given space of predictors. And as such, we cannot expect machine learning to go beyond the intrinsic limits of predictability of the atmosphere. The atmosphere remains a chaotic, nonlinear system. Lorentz was right in the 60s in his estimations that we cannot go beyond certain limits. And the archives will never be long enough, especially for extreme events that are extreme by definition. Otherwise, they would not be extreme anymore. So, of course, having larger data sets is good for machine learning, but we cannot expect to have a perfect model. We always have to represent the remaining uncertainty in the appropriate way. And with this, I thank you for your attention. I see there are only a few minutes for questions, but I will be available also tomorrow during the discussion panel session. And I thank you for your attention.
Thank you very much, Loris. Great presentation. I believe there are some questions on the website. Is anyone that is in the speaker room wants to start asking the question that was listed? Okay.
Yeah, since I am here, I can ask my question.
Yeah.
Mm-hmm.
Thanks for the great talk. So I have a more general question because PySteps is a really great tool and it's completely open source. So maybe you can comment also from the perspective of a Met service, how and why did you choose to go this way, using open source, committing to open source?
But the choice was quite spontaneous, and at the beginning we didn't really realize that it would become so big. So there was a Seppo Pulkkinen, a Finnish, who came to visit MetaSwiss for 2 months, and we had to organize a nowcasting course for the ERAT conference in the Netherlands. And we said, okay, let's do some practical exercise in Python. Daniele Nerini, my PhD student, was also having this cascade decomposition from steps in Python. Seppo had a similar implementation. So we said, okay, let's make a common repository. And we say, since we are doing just science and nothing like operational for the moment or nothing big, let's go on Git. And then only later on, we actually formalized the process within MetaSwiss and said, okay, now we have an open source project, and they approved it and they are happy. So we have some resources for it. And it was very nice because suddenly we had people contributing also from McGill, some ex-collaborator from Australia. Some were more focusing on the science, some were more Python experts, and they added continuous integration and unit testing and things that usually you tend to leave aside as a scientist. So we started small, and now it grew, and it became a nice platform. It's nice for research, but also we noticed that several weather services started to use it also in real time, and this is a nice outcome. And also there, at some point, we had to change the license. We started with the GNU public license, and then we received a call, and that, yeah, but it's a bit like a virus, so then we are obliged to use a GNU public license in all what we derive from PySteps. So we changed to the BSD license so that you can also develop commercial applications if you want. You're more free with this license. And so far, it seems to be working well.
Okay. Thanks.
You're welcome.
There is many questions, which I'm happy to see that, but I think I will pick 2 questions right now, and I will leave the remaining for the end of the session for discussion. So we have a question from Wang Chunhu from Hong Kong Observatory. Thanks for the interesting work. We have also observed that deep learning nowcast tends to forecast a smoother prediction field. One of the reasons I suspect is that the cost function did not sufficiently encourage predictions of heavy precipitation. Any suggestions on how to explore further?
Yes. So this is also one of the approaches to kind of counteract the smooth predictions. There are some experiments in the paper of Gabriele Franch where he weighted the error committed on high precipitation rates more. And then he also stacked different machine learning models trained on different precipitation thresholds, trying to have a better performance on high precipitation rates. But even with that, we still end up with a precipitation field that is a bit less smooth, but is not yet realistic. It doesn't contain the variability of the original radar fields. Another approach is this R-gun. There was a paper, I think, in the table before. It's a deterministic gun that preserves the variance. But even then you get only one realization, and we know that the atmosphere is chaotic and there is uncertainty. There is some irreducible uncertainty. So I really suggest to generate ensembles of realistic precipitation fields. If you're already at the point of training deep convolutional neural networks, the step to generative machine learning is not that big, and I strongly advise to go into that field and then to use classical probabilistic tools for verification to see if the ensemble is spread is large enough, or if it's under dispersive, if the probabilities are calibrated, and so on.
Good. Thank you, Loris. I will read one more question before we move to the next speaker. And this question is, by the way, I'm picking the highest rated ones because this is what we agree. So we have a question from Clement Zimmer. Great talk. Numerical weather prediction becomes the dominant predictor already after 10 minutes. Can we conclude that numerical weather prediction will eventually outperform nowcasting already for 10 minutes forecasting?
That's a tricky question. I would be a bit careful in doing that statement. That was the importance of predictors in the nowcasting model, but in that slide we didn't show a comparison of the ability of the NWP to predict the TRT, the thunderstorm rank, with respect to the ability of the machine learning to predict the thunderstorm rank. And the same if you do an intercomparison radar extrapolation with or without machine learning against NWP, you see that usually in the first hour it's difficult to outperform the extrapolation nowcast. So that was just in terms of variable importance. If you want to beat radar extrapolation within WP, we really need a very high rapid update cycle. Now we go hourly usually, but radar images come in every 5 minutes, and thunderstorms evolve quite fast over 5 minutes, and we need an appropriate radar data simulation scheme. And also there are some fundamental issues that basically it's difficult to pull the WP model so close to the radar observations to start from very good initial conditions because of model imbalances and things like that. So I don't think it will happen in the next 5 years, let's say, but who knows?
All right, so good. Thank you again.
You're
Could
welcome.